Hi, my name is Daniel Coelho, and I'm a product manager in Azure Synapse Analytics. I work on the Apache Spark experiences in this Azure Synapse platform, and I'm excited to bring to you all an in-depth view of it in this Data Platform Summit 2022. Here's what we're going to cover in the session. First, I'll go through a primer of Apache Spark on Azure Synapse, going through the main architecture and some key concepts and differentiators. Then I'll step into those features and showcase scalability with auto-scale and dynamic allocation, read performance with the intelligent cache, SQL Analytics integration using the accelerated connector in its latest updates. Then we will switch gears and we'll cover some exciting new features that came out with the newest Spark 3.2 runtime, such as the Delta Lake 1.2, a new feature that aims to minimize the small file problem, adaptive query execution for query performance, and the Pandas API on top of Spark data frames for easier workload migration. Then we will wrap up with the runtime lifecycle and supportability and some recent announcements. We do have a lot to cover, so let's get into it. In this section, we will quickly go through what the Azure Synapse Analytics is and how does Apache Spark work on it. So what is Azure Synapse Analytics? Azure Synapse unifies your data tasks, and your data teams with an analytics service that does it all. Modern workloads do require both SQL and Apache Spark, so we built a cloud-native analytics service engine that converged the big data and the data warehousing so they could achieve limitless scale on structured, semi-structured, and unstructured data. So at its heart, simplicity at scale. You unified the platform for everything. So we provide a single pane of glass for management, monitoring, and security. We do serverless analytics runtimes for data at any scale. And we do have low-code experience for data analysis and the citizen data scientists and data engineers. We won't talk in detail about this huge diagram today, but it is important to position Apache Spark in the context of the bigger picture and the scenarios we're solving for. The main takeaway from this slide is that we prime Apache Spark as a key OSS compute engine for data ingestion, data movement, data preparation for BI and ML scenarios. We made it serverless, we made it secure and integrated and optimized for the Synapse service, so we don't have to worry about it. Now, let's go through the two most important concepts of Apache Spark on Azure Synapse: the job service and the Spark pools. We're going to hit Spark pools first. So what is a Spark pool? A Spark pool is just metadata. So it is a configuration or definition on how you want a Spark instance to look like. So it is exposed as an Azure resource. You can create it either from the Azure Synapse Studio or directly from the portal. So it's exposed there once you created it. For customers, it looks like a Spark cluster. It contains definitions such as which Spark version you're going to use, the library management and the additional libraries you want to load, the library versions and the components under the hood that you are carrying on that Spark pool definition. And you define also the scale parameters for that Spark pool, such as how many nodes you want, the kind of VMs that you want to use for their Spark sessions. That methodology provides you some isolation and budget control, mostly because it's just metadata. So it's free. It's defined there. It will live as a resource on our Azure portal. And you're not paying for anything unless you're actually submitting jobs or notebook executions through it. So you can have as many as you want. So it is secureable, so you can provide additional layers of security on who can actually use that Spark pool. As I mentioned before, you can have libraries installed, different libraries for different pools. That's a way for you to provide workload segmentation between different teams, and very specific libraries on different pools, different sizing requirements. So it's most likely that you're going to have pools for your production jobs, pools with different parameters for experimentation for your data engineering teams and for your data scientist teams. You can pretty much govern the pools pretty much in a way that fits your organization. And I think one most important feature is that you're not defining a precise cluster. It's a definition on how you want your Spark workload to be. So now that we discussed a little bit of the pool, so capture this metadata that defines how your Spark workload is going to be, and let's move forward on how to actually execute it and how that happens on Synapse. Let's say that now you have a pool defined. You log into Azure Synapse Studio Workspace UI, you create a new or you import a new Jupyter notebook into it. Then you configure it by attaching that notebook to use the pool that you just defined. And then you start rocking some spark.read commands. So how does things get executed on Azure Synapse? As you click run for the first time, the following happens. And this is a very complex workflow. I'm gonna just go through it, but this is pretty much the surface that we expose that's called the job service. That's the serverless abstraction on how to execute jobs, Spark jobs on Azure Synapse. So you have a notebook with Spark read commands, you click run for the first time. Let's say that's the first time the Spark pool does not have any running jobs. So your notebook client gets a token with AAD to establish this relationship between the user and the workspace and your session, and requests a session create for the Synapse Gateway. Synapse Gateway controls everything. That's the exposure surface that we provide to notebooks and Spark jobs. Synapse Gateway then authenticates and validates the request and forwards down the path to the Livy controller, if it exists, hosted in the front end. Then the front end forwards a request to the back end to create the jobs. One for creating the cluster if the cluster is not already there, and the other for creating your Spark session. Then there is this conversation between the front end and back end that makes sure that the resource providers obtain the details from the pool definitions and delegates back and forth until your cluster is set up. I know I mentioned before there is no cluster. There's no cluster for you. But as long as the pool lives, there is a cluster that is controlled by this all these components to make sure that only through the duration of your request and the timeouts that you define in the pool, the cluster is going to be alive and answering back to your request. And as soon as either the timeout hits or you kill it explicitly, then the resources are deallocated and you start paying for those. So this back and forth goes for some time until your instance is created, you're ready to run commands, your Livy's endpoint is ready to go, and then the notebook client starts sending commands back and forth. So there's a huge link established between your notebook client or your job definition or your pipeline all the way to the Spark cluster, and there's all these hoops in the middle that controls security, resource usage, monitoring, and etc. So as you go, additional cell runs or new job submissions that are established to run within that pool for your user in that workspace are gonna just use the session that's already established. So it's not for every command you spawn a whole new group of resources. You're going to be used and attached to that pool for as long as the pool lives. So let's summarize. Spark pools definitions and the job servers work together, right? You will submit a notebook, Spark job definition, submit execution through to the job service using the Spark pool definitions that you made before to run the workloads. Session persistence and share resources happen naturally while the pool is running. A good way to achieve workload segmentation is to use multiple Apache Spark pools, providing the flexibility and great resource usage control. So most likely, you're going to have pools for running production workloads with very defined parameters that go required by that workload. And you're going to have different pools for experimentation, for data science, and that's completely different with different libraries, different Spark versions to be used by different teams. And remember, it is free, right? So it is a free resource, as many pools as you want. You only pay when you're using those pools. Remember that Apache Spark on Azure Synapse is an open source Apache Spark, and we actively contribute back. The Synapse team does add feature enhancements, and we're going to talk about some of those enhancements here, but mostly we integrate into the Synapse platform and we provide additional security around Apache Spark, which is very important. Just closing on that thought, Synapse Spark Pool is just metadata, is lightweight and free. And it's also a serverless job service. So there is no persistent cluster. You're only paying for the resources while you're using it. Thank you. Now let's talk about two important features of scalability, which is auto-scale and dynamic allocation, and how they behave on Azure Synapse. So auto-scale is a configuration set that you do for your Spark pool that basically controls the minimum and the maximum node configuration. So as soon as you define that, you start running jobs within that pool. Some metrics are going to be dynamically monitored, and there's a logic that's going to decide whether the cluster resources are strained and they're going to go up or down. So the number of nodes where your Spark job is running is going to scale up, and then as soon as you stop running them, it's going to monitor resource usage, and then it's going to scale down. So auto scale is about the number of nodes. So you can define pools like more suited to data experimentation or data scientists. You want to give those people, those team members, a lot of headroom. So you define a pool specifically for them on a specific Spark version, and you enable auto scale up and down. You're going to know exactly how much money their experimentation process is consuming. As an additional feature is dynamic allocation of executors. So for a Spark cluster with 3 nodes or 5 nodes, then you can also enable the dynamic allocation of executors. So you can make it static. Every executor on that cluster configuration is going to run with the same size and whatnot. This more suited when you know the workload very well. But when you don't know, you're working through experimentation, you just enable dynamic allocation and let the cluster figure out how big your executor size should be. Just remember that autoscale and dynamic allocation can work together, so you can have a mix and match of both, but they are somewhat independent. They are very optimal for variable workload scenarios, as I mentioned before, as data engineering and data science experimentation workloads. But when you're kind of migrating very well-defined Spark jobs that you know exactly how much resources they consume, or after the experimentation phase where now I know that how much, how many nodes and how many allocators executors I need to run that specific workload, and you're migrating that workload to a separate pool, then you can have like a more controlled pool just to run a specific job, and you're gonna pay the exact amount of money that that your budget allows for that kind of production workload. Now let's take a quick look on how autoscale would apply on a specific Spark pool configuration. Now we have a Spark pool defined with a minimum of 3 nodes and a maximum of 5 nodes, and you start running a job. So you have this concept of the base node set and the kind of reserved additional nodes. So those additional nodes are not allocated as you start, but then as soon as the application Spark session 1 with medium executor starts executing, it goes forward and starts consuming resources. That session 1 might get expanded to use the additional nodes. So you can have a scenario where a single application might take up the entire Spark resources. If you kind of start maybe at a second session on top of the same Spark pool, you're logged into your workspace, you fire up a second notebook within the same workspace, you might well submit additional jobs, and you need to be aware that how those resources are going to be shared. So you can also, instead of kind of using bigger allocation, you start doing a lot of small experimentation with small executors. That's fine. You just always need to be aware on how those things are going to play when you're allocating execution resources. Another example is that, okay, now I get to the point where I have 2 sessions, I have 2 different notebooks, or maybe 1 notebook and 1 Spark job running, and they just have different configurations. So everything that I'm saying can be used either on static executor allocation, or it can also be done with dynamic executor allocation. Now we're going to talk about a feature more related to read performance. So we came out of scalability. Now we're going to talk about how to boost read performance by using the intelligent cache. The intelligent cache is an Azure Synapse Spark feature that tracks the reads of Delta tables, Parquet files, and CSV files coming out of ADLS Gen 2, and caches those files on fast storage, on local disk storage across all the worker nodes. So, and it also has intelligence to refresh the caches when the files are changed, and controls the cache with more recent data. So it automatically purges old data and just keeps the latest data in the cache to allow a faster read performance on those kind of tables and files. But you might ask that, okay, how is this different from the cache keyword that we have available on Spark and Delta Lake? So it's a local disk cache. So the cache from Spark is more like targeted for in-memory. You actually explicitly need to issue the cache command. If the data changes underlying, you need to refresh the table and then cache it again. So the intelligent cache doesn't require you to issue any command. As you're reading data from a remote ADLS endpoint, which is the case, it tracks the data that you read and makes sure that the data goes into the local disk cache, so subsequent reads to that same data is faster. But additionally, you can also still use cache to cache in memory, right? So you just need to be aware of the differences when you're defining a cache strategy. The good thing about the intelligent cache is there's a configuration option. So you basically enable intelligent cache within the Spark pool definition. You define how much storage in terms of percentage of local disk storage you want to use for the intelligent cache. Our internal benchmarking shows off, and some customers see the added value benefit of a lot of jobs that just read the same data over and over again. It may have performance benefits between 50% to 65%. 50% is more like CSV files, more close to 65% is more like Parquet files on the subsequent reads. We do recommend that you start with a cache setting of around 50% and adjust accordingly. Workloads that do have excessive shuffling or already require a lot of disk space do need to account for the use of the cache. So if we already have a workload that writes locally a lot within the workers, or you have too many loaded libraries within the cluster, so you need to do a proper math and understand how much cache you can safely configure to your Spark jobs. One great value proposition of Azure Synapse is the integrated experience. Let's now talk about the native integration between Spark and the SQL universe. And let's talk about more specifically about this SQL Analytics connector. First of all, what is it? So it is shipped with the Spark pools. And it's an integrated connector library that enables very fast transfer of large data sets between Apache Spark and the Azure Synapse dedicated SQL pool. This is one of the top requested features in terms of enhancements that we have tracked with our customers. We significantly improved that feature within the latest releases of Spark 3. And it does that by having a distributed design. So all the Spark executors are going to talk directly with the SQL data warehouse engine in parallel. So it allows very efficient and very fast load and read data from and to Spark, right? So on scenarios where you use Spark to ingest and form your data lake, you perform data transformations, you consolidate your tables between the medallion architecture of bronze and silver. And as soon as you're done, we have a lot of scenarios where the data needs to be moved and to a SQL endpoint to be served to the BI analyst and additional query. SQL Data Warehouse is excellent to provide more concurrency scenarios on top of big data. It's not as batch oriented as Spark is. So it fits nicely into that scenario. So what basically we brought with the new version of the connector? The write modes, that's where we got most of our feedback. The write mode now is using the copy functionality. And the performance was night and day when we moved in that direction. So we use native copy commands on the SQL engine now to batch load the data. We also now support an overwrite and the append methodologies for load. Before, the engine using an old methodology, and you needed to go back and forth between the T-SQL endpoint and issue kind of SQL commands, and then you need to go back to Spark to do things. Now we can do everything that we need to do by just using the proper write mode on the Spark.write commands. Namely, I think Spark, the mode override is the biggest one that customers have been asking for. We also providing append, error if exists, and ignore altogether. So it's a very thorough way of, a very Spark way of actually dealing with external data sets, and now with excellent performance, very native integration. The connector is shipped by default in our engines, so you don't need to do extra configuration to get it working. Another feature was now the read mode supports SQL views. Initially, it did not, so you can kind of understand what kind of problems we were having with this. So now all the abstractions that are created in terms of views in the SQL dedicated pool are now available through views, and the Spark.read kind of support that natively now. And the last one is that before we only expose that functionality through the Scala API. So imagine that you came through coding on a Python notebook, on a PySpark notebook, and then you needed to switch back to Scala, and with the change of syntax, with the pitfalls of using Scala. But now we deliver the full Pythonic support for the connector on the Spark 3 or greater runtimes. So up to this point, we went through concepts, an architecture primer of Synapse, how Apache Spark works on it. Then we took a look at the integrated features in the platform, namely the intelligent cache and the SQL connector. We do have many other features under the hood ready to be used. I encourage you to take a look at the Azure Synapse Analytics documentation to understand what's under the hood with Spark and all the connectors and all the performance features that we ship. But now let's discuss what's new. So recently, roughly a month ago, we released the Azure Synapse Pool for Apache Spark 3.2. So that release publishes a new endpoint with containing Spark 3.2 that contains mostly Delta Lake 1.2 that provides the following kind of functionalities. One is basically column skipping based on statistics and generated columns. The functionality of restoring to previous versions of the Delta Lake table. Column renaming. Column renaming has been there for a long time, but when you rename the column before, it kind of required for the full rewrite of the Parquet files. If you have a petabyte table, you would be in trouble. You had to plan your renaming strategies. Now it's a full metadata operation. And we improved the optimize command to perform even faster. On top of Delta Lake, we shipped a feature on this release called the Delta Lake Optimize Write. The Delta Lake Optimize Write is tries to solve the small file problem. One of the oldest problems within the distributed compute engines of the big data universe, coming all the way back from the Hadoop times, is that when you write constantly very, very small files, either Parquet, and you have a table defined on top of this, the distributed engines actually require and they prime larger and very constant size files, so the engine can actually calculate the distributed query pattern efficiently. So when you have skewed file sizes, or in terms of size, or in terms of number of rows, and bad distributions over partitions, so the distributed engine has a tough time in providing very accurate performance. So coming out of the feedback that we work with our customers, we have been developing this optimize write feature on top of the Data Lake that does an additional shuffle within the write to maximize the file size during the write, so we get more leveled files. You can control that feature in many aspects, but that's a very, very good feature for streaming ingestion or data lake formation ingestion that you need to land the data with more structured file sizes, so the read patterns are more optimal. That feature is available on Spark 3.2 pools. One coming directly from Spark 3.2 is the adaptive query execution. It's a dynamic query optimizing plans that focus on runtime statistics to rewrite the plan and perform a bunch of different optimizations like skew joins, substituting sort merge joins with broadcast joins or different kind of joins. So it really tries to boost performance. It is turned on by default on Spark 3.2, even in the open source project. And it does a very good job in actually rewriting the query execution plan to perform better. And lastly, this is mostly a migration reduction friction feature that data scientists really ask for it. In the past, if you were used to using the Pandas API to develop using scikit-learn and whatnot, and then you had to move to Spark, the APIs of Spark data frames, especially the Spark ML on top of data frame, are vastly different on what the Pandas API did. So a couple of years ago, there was a project called Koalas that started to port a layer of Pandas API compatibility on top of Spark data frames. That has been promoted as a first-class experience now. So basically today, if you get Pandas-oriented code, you can more easily bring that code into Spark, and basically your data frame that was a Panda data frame is now a Spark distributed data frame. So that functionality is mostly about reducing friction on migrating workloads towards Spark. The technology still has some limitations. There are some scenarios of UDFs and some things that still don't work, but it's miles ahead, and it's most of the very, very common scenarios, especially when you're moving back and forth between Pandas and Spark data frames, is just now works out of the box. In this last part of our session, let's talk about a little bit about the Azure Synapse runtime for Apache Spark and its life cycle. Up to this point, I haven't been discussing what the runtime is. There is a relationship between the definition of the pool and the runtime. So a Spark pool is defined to use a specific runtime version. When you define the runtime, basically puts together all the versions of all the components, being the languages of Python, of Scala, of the JDK, the main libraries, the main Hadoop libraries, the .NET libraries, the Delta Lake libraries, and the Python libraries, and all the libraries that we carry, and all the library versions of the connectors. It's a pretty straightforward concept. So when you define the pool, you're actually linking that pool to a specific runtime version. If you want to understand what's under the hood, you need to go to the documentation side of Azure Synapse and just look for the runtime release notes, and there you're gonna find all the components and all the library versions that you're gonna be using when you configure a Spark pool to use a specific runtime version. So now that you understand the relationship between the pool, which is metadata definition, and you say, okay, this pool is going to use our Synapse Spark runtime 3.2. I know everything is under the hood. So when I create the notebook, I'm going to have those libraries readily accessible with all the connectors and everything pre-configured. That's awesome. But from a sustainability and supportability standpoint, it's very important to understand the life cycle of such runtimes. Over time, Spark gets new versions, and the Spark project has a very aggressive methodology in terms of releasing a new Spark versions. And Microsoft and the Azure Synapse team needs to keep pace by releasing new versions. But we also need to be very clear on the supportability and the retirement path for each of the very old versions. So within our documentation, we do have the life cycle policy, which I'm going to give a quick highlight on how that works now. So when you take a look at our documentation, you're going to find this diagram. So this diagram is about showing off how the Azure Synapse team is going to handle each of the runtimes. So as soon as the Spark project kind of releases, we try to meet the bar in terms of releasing a preview runtime for people to use on their Spark pools. During the preview state, the runtime is mostly targeted as experimental. We might upgrade libraries, and we most likely will upgrade libraries and change version of stuff. And we're going to capture a lot of feedback and metrics of stability for customers. We release the preview runtimes with the intent that customers validate workloads before they migrate to a new Spark version. So to make sure that the workload now works with the new version, and maybe all the libraries that we're going to change for the new version. The preview time frame can varies between 1 and 3 months. And then once it reaches the stability standpoint, we move that runtime into GA. So after this point, the runtime is generally available to all customers. Full supportability and SLAs for Azure services apply. And the runtime is going to be within that GA state for a minimum of 1 year. What happens at the end of that year is that if a runtime has the metrics of stability and popularity and usage, we might decide to move that library into a long-term support state so customers have one extra year there. What happens either at that 1 year mark or the 2 year mark is that every runtime is going to pass through an end of life announcement state. So at that point, we notify all customers that, okay, we've been supporting this runtime for 1 year or 2 years, and now we are announcing that it's going to be retired. From that point on, the runtime still is going to be supported, but we're going to do a reactive approach in terms of applying patches. Of course, we're always going to apply security patches on top of that runtime. But consider that gray area, the gray arrow there, as the exit ramp the customers need to start preparing to move to the next version of Apache Spark. So we have this very well-defined 5 stages of the runtime: the preview stage, the GA stage, the long-term support stage, which is optional, an end-of-life announced stage, and then once the runtime gets to the end of that period, that can be as long as 3 years and 3 months, then the runtime is going to be desupported and retired. So by having a very well-defined life cycle and support policy, we can create a sustainable methodology to govern Apache Spark for corporations on top of Azure Synapse. So we can provide a stable platform with very well-defined parameters so customers can run their workloads safely and securely. We have covered a lot of ground in this session. We started with an architectural primer. Then we moved into talking about what a Spark pool is, the job service, how to run jobs, what happens when you run jobs in Azure Synapse. Then we talk about two very important features that we have, the SQL connector. the intelligent cache. There are many other features under the hood to be explored. We have .NET for Spark. We have hyperspace indexes. We have many others. So please exercise curiosity and take a look at the documentation and see how to make Apache Spark under Azure Synapse work for you. Then we moved into what's new and what we're doing to make our experience the best experience, the Spark experience, with the 3.2 version, with Delta Lake and all the other things that we discussed. And then we closed by talking about the life cycle and supportability and how to keep your Spark workloads secure, supported, and moving forward within Azure Synapse Analytics. With that, it brings us to the end of this session. I'm still available in the chat or the Q&A box to answer more questions or to connect in the virtual networking lounge. I'd like to thank you very much for your time.